In this video, we will explore how to construct a confidence interval for the population correlation coefficient and explain why Fisher's transformation is necessary in this process. When we examine the sampling distribution of the sample correlation coefficient, we observe that when the true population correlation is close to zero, the sampling distribution of the sample correlations is roughly symmetrical and bell-shaped, approaching a normal distribution as the sample size increases. In this case, the distribution is centered within the -1 to +1 range, and the boundaries have little effect on its shape. However, when the true population correlation is close to +1 or -1, the sampling distribution of sample correlations is skewed. This is because the sample correlation coefficient is strictly bounded between -1 and +1. When the true population correlation is close to one of these limits, the distribution of sample correlations cannot spread out beyond that extreme and creates asymmetry in the distribution near that boundary. To address the correlation coefficient's boundary limits, the inverse hyperbolic tangent transformation, or Fisher's transformation, is used, which converts the sample correlation coefficient into a new variable. This plot visually compares Pearson's correlation coefficient with its Fisher's z transformation. When Pearson's r is near zero, the Fisher's z transformation is very close to the r. However, as r approach -1 or +1, the transformation significantly stretches the scale at these extremes. This transformed variable shows an approximately normal sampling distribution, largely independent of the true population correlation and the sample size. A health psychologist is investigating a potential link between the average daily screen time and the quality of sleep among teenagers. He hypothesizes that increased screen time is negatively correlated with sleep quality. To explore this, he recruits a sample of 40 teenagers and finds that the Pearson's correlation coefficient between average daily screen time and standardized sleep quality index is about -0.48. The psychologist wants to construct a 95% confidence interval for Pearson's R. To do that, the psychologist will first use Fisher's z transformation to convert R into a new variable z, using this formula. For a correlation of -0.48, the calculated z value is approximately -0.523. This z value serves as the point estimate of the sample statistic. The standard error of z does not depend on the value of the population correlation, which can be calculated using this formula. For a sample size of 40, the standard error is approximately 0.1644. The critical z-value for a two-sided 95% confidence interval can be obtained from the standard normal distribution table by locating the value that corresponds to a cumulative probability of 0.9750. The intersection of the corresponding row and column provides the critical z-value, which is approximately 1.96. Now, inserting these values into the confidence interval formula, the lower limit is -0.8452 and the upper limit is -0.2008. To convert these confidence interval limits back to the R scale, the following formula is used. The lower limit for the population correlation coefficient is approximately -0.6886, and the upper limit is approximately -0.1981. Therefore, we can be 95% confident that the true population Pearson's correlation coefficient between average daily screen time and sleep quality index scores among teenagers lies within the interval -0.6886 to -0.1981. Because the calculated 95% confidence interval doesn't contain zero and includes only negative values, it supports the psychologist's initial claim of a negative relationship between screen time and sleep quality. If you like to test your knowledge on this topic, check out the link in the description below or visit our community page.